So hopefully you're in the right place. So this is a PyGeoChemCalc workshop. So we've written this code collaboratively with Dapo and I'll introduce ourselves in a second here, to calculate thermodynamic properties of waters, aqueous species, solids, and gases down to deep earth conditions. And also we can use this code to do all kinds of fun things like generate new thermodynamic database for popular geochemical modeling software, things that you might have used like FreakC or GeoChemist's Workbench or reactive transport codes as well. So we're going to try to give you at least an example of how to do all of this stuff today. And then again, at any point, that's kind of a goal today, is to make sure that you have the ability to ask us questions throughout the morning, and then we'll be done at noon. So hopefully you can enjoy the rest of your day here in Montreal. So I am Ben Tulo. I'm a professor at the University of Calgary. This is my colleague and friend, Dapo Alalayo, and those are our two friends that we met at the Forbidden City in Beijing last fall. And we are the two main developers of the PyGeoChemCalc code. So the code originated with a bunch of stuff I wrote as a PhD student in MATLAB, and then during the pandemic, Dapo was locked in his basement and I think decided to convert it to Python, and then that's how we ended up releasing the code to be what it is today. It's always being adapted, so some of the stuff we're going to teach today is actually new within the last month or two that we've added to the code as well. Okay, so here's a schedule, and again, I just put general times on here so that we can be as flexible as we want with folks learning how to do things. But what we're going to do is start with just an introduction to thermodynamics and PyGeoChemCalc writ large. So if you have never used Python before, hopefully using the Colab notebooks and Gemini can help you as well on Colab notebooks. You'll be able to get through that first part, no problem, because we've already answered those problems for you, but then everything else is sort of set up as word problems, more or less, so that we have a prompt, and then what Dapo and I are going to try to do, and we've got some helpers in the back, Serhat, mostly a PhD student from University of Calgary, who can help us try and do this stuff with you, so we'll make sure that everyone's learning how to do what they want to do with the code. So from there, we're going to go into introductions to how we calculate thermodynamic properties of minerals and gases, and the revised Helmholtz and Kirkham-Flowers equation of state for aqueous species, and those are all in that Jupyter Notebook practice general.ipynb. And then around 9:45, we're going to shift into the first sort of more difficult exercises of the day. So introduce you how to calculate solid solutions of, for example, the minerals olivine and pyroxene and plagioclase, how we calculate thermodynamic properties from clays. And so actually we've invented ways of calculating them based on, the microprobe data that you might have for some clay minerals, and then also estimated thermodynamic properties of glasses as well, which we've only recently added to the code. So that's in that solid solution problem.ipynb. We'll take a break somewhere in there, and then 10:30 we'll have a introduction to how, if you have new thermodynamic data, know that we had folks come up to us before the session today. If you have new thermodynamic data you want to add to your favorite software, for example, if you're modeling with EQ36 or GeoChemist's Workbench or FreakC, and you've found some data in a paper out there, you want to put that into your database. How do you do that? We'll show you how to do that with the database problem.ipynb. Towards the end there, 11:15, we'll give you an intro into hydrothermal vent geothermobarometry. So we actually use quartz geothermometer, chlorine geobarometer to calculate temperature and pressure of a reaction zone at a mid-ocean ridge hydrothermal system. And really that exercise is just an example to show you what this code is capable of, even if you don't particularly care about mid-ocean ridge hydrothermal fluids. And then lastly, we'll just show you that you can actually now use PyGCC directly to generate databases and run FreakC, for example, or GeoChemist's Workbench, whatever you'd like, in a totally scripted function. So you can actually imagine the possibilities there of having many simulations run with new thermodynamic data based on temperature and pressure. So that's what we're going to do. We've only got 3 hours. We did that intentionally because we don't want to scare you off of the code by just drilling you all morning here. But hopefully over this time, you will get as many examples as you need to show the power of the code, and then hopefully over the next bit of time, you'll be able to use it. Okay, so this is just the structure of PyGeoChemCalc. I'm not entirely sure how that ended up down at the bottom of the page there. So we have all kinds of functions. So this is like basically a list of the many functions or many of the functions in there. So we're going to go through how to actually use these things today, but you'll see things like DB reader. So how do we actually get thermodynamic data? This is like Gibbs free energy, enthalpy, entropy, heat capacity, and so on. How do we get that so that we can actually use it? That's what we have to do with the DB reader. There's various codes, bits of code for calculating thermodynamic properties of water, and I'll talk about why that's important in a second. Calculating the log K of various reactions needs also, for example, ways of calculating thermodynamic properties of minerals and gases, aqueous species, and solid solutions potentially, and clays potentially. And then ultimately, the original goal of this code was to write databases for various modeling software, but obviously that's just one example of what you can do with it. You can you'll see all morning how you can actually just calculate thermodynamic properties and understand a lot just based on the thermodynamic properties themselves. Right. Okay. Before we really launch into this, I want to make sure that everyone had a chance. Hopefully, I was given a list of emails. Hopefully, you were all on that list of emails. Hope you had a chance to download the notebooks. Anyone not get that? Okay, great. Okay, so I like this quote because hopefully you've all felt this too. It's possible to know thermodynamics without understanding it. So I'm going to give you the absolute bare minimum examples of the equations that we're going to be calculating today. If you like to talk about these things, I am obsessed with them. So if you like to talk about them while we're doing the examples, please do just reach out and ask. Otherwise, we're going to gloss over most of the details. And if you want to know more about this, so this is a really good textbook for fundamental thermodynamics. This one's really good for geochemical thermodynamics, about basic stuff. And this one, which is hard to see, by Greg Anderson and David Creer, is also really excellent as well. It's a bit more thorough. Okay. So our philosophy for teaching today, for using PyGCC, is learn by doing and never do anything from scratch unless you absolutely must. So the only person that should have ever done these things from scratch are me or Dapo. Everything else should hopefully be an example. And if there's an application that you think is possible, that it doesn't exist as an example yet, let us know so we can do that, and then we can put it on the read the docs page, and so everyone can have that example as well. And then also, I'm sure you've probably heard this Zuckerberg quote in the bottom here, regardless of the man, I think I like the quote, move fast and break things, right? The whole point is that you're not going to blow up your experimental reactor by messing up some code, right? All you're going to do is it's not going to run, it's going to give you an error, and then we can figure out how to do it. The examples we do today are designed to make sure you never have to do anything from scratch. Okay, another nice quote about thermodynamics. It's not difficult if you can just keep track of what it is you're talking about. So hopefully with the next couple of slides, it can show you what we're talking about so that we can get much more complex as we go. Okay, let's start with the thermodynamic properties of water, since this is largely a aqueous geochemical modeling exercise code, but obviously we can do minerals only as well. So the equations for calculating the thermodynamic and thermophysical properties of water are complicated. They're not the kind of thing that you can just code up in a spreadsheet and get to work. They're the kind of thing that requires some iteration most often, and sometimes lots of iteration if it's near the critical point and so on. And so one of the big things that had prevented me earlier from just releasing the primordial version of PyGCC to the public was the water equations of stakes. I was using one that was not as good as the one that we have now, and I think that was the biggest struggle for DAPA, was getting that to work overall. By using and combining these equations, we can determine properties such as density, the dielectric constant of water, and the delta G of water, all of which are important for calculating thermodynamic properties not only of water, but also for aqueous species. There are four basic types of problems implemented in this class function, IAPWS 95. So IAPWS is the International Association for the Properties of Water and Steam. 95 is sort of the most recent, generally agreed upon equation of state for water. And so that's what we use in our code as well. And obviously the thermodynamic properties of water haven't changed much over time, but what this has allowed us to do is get closer and closer to the critical point, and then also with expansions to higher pressure and temperature for the deep earth water model as well. So basically the way that this works is that we have to have the variables temperature, pressure, or density. You need two of the three to get there on and off the so-called steam saturation curve. So density of water, why does it matter? So here is just a calculation done with PyGCC. We're all going to do this in a second together, but you can see here density drops off there. What's happening there as we go from temperature of about 300 degrees to 450 degrees? What happens to why does density go down? Pardon me? Yeah, that it's boiling, right? That's all that's happening there. So you can imagine that we need to know this kind of thing in order to actually calculate the thermodynamic properties correctly. And the Helgeson-Kirchhoff-Flowers equation of state is canonically shuts off at 0.35 or 350 kilograms per meters cubed. And beyond that, we have to do something else, which we'll show you. So this also goes into our calculations of the dielectric constant. So this is, theoretically the ability of water to split solutes or molecules into ions. So you can imagine hydrochloric acid is almost all split into H pluses and Cl minuses at low temperature and pressure. At high temperature and pressure, it complexes to become HCl aqueous. And that's calculated or known based on the dielectric constant. So the Helgeson-Kirchhoff-Flowers equation of state incorporates the dielectric constant in order to do those sorts of calculations. So just a broad brush example of why this matters. So this is a paper from Bill Seifried and Kong Ding from the University of Minnesota. Basically, what this is trying to show you is that the classically assumed thing about black smokers at mid-ocean-rich hydrothermal systems is that they're highly acidic fluids, right? But that's only at room temperature, right? That's only at 25 degrees Celsius. If you actually measure it, so they invented this device that it can actually measure pH in situ, or you can calculate it. So that's the various hashes here. So that's the predicted one, sensor one, and then also the pH neutrality. You can see that actually the pH in situ, so at 384 degrees, for example, of this vent fluid at P-vent is actually almost neutral, right? So actually in situ, these solutions are not particularly acidic at all. And it's only acidic once all of those HCl's in solution become uncomplexed to become H pluses and Cl minuses. Okay, so with that extremely rapid introduction, we're going to do our very first examples here with PyGeoChemCalc. So we're going to use it to calculate the properties of water, right? So that is the basis for almost everything else that we do. So for this first one, at least, we've already solved the problems for you. So I hope that I can just switch to that tab and show you how it goes. So open this file. Practice general IPYNB on Google Colab or whichever Python distribution that you're using. And then we're going to do this IPWS example. So it's in notebooks. So in there's a bunch of goodies, but practice general is the first one. And it looks just like a regular old file, but when you double click on it in Drive, it opens it as a file. Is everyone able to get that open? Please do let us know if you can, because we don't want anyone to just struggle the whole time. Okay, so we can go through what this is doing for us. So you can see right away, pip, if you're unfamiliar with pip, it's a way of installing modules like PyGCC from a distribution that's online somewhere. So pip install PyGCC and then upgrade it. So as I was saying, we're constantly updating the code. Sometimes updating the code also breaks something. So we do like whenever you let us know that as well. But you have to install it on here because this collab is running on basically a fresh computer every time you open it. So we're reinstalling it each time. So and it tells you what it's doing. So it says I'm going to download PyGCC. Fortunately, this is not a particularly giant package, so it goes pretty quickly, successfully installed. And then it's, do we have all these other modules that are needed? Things like NumPy, Pandas, SciPy, etc. And then the next one, we can now import. So if you're unfamiliar with Python, now that we've installed it, we also have to import it so that we can actually use it. That's what's happening there. And then the next thing is check all the functions. So this main function name PyGCC then gives us all the functions that Dapo has spent his whole life writing. And then we can help. So anytime that a function exists, there's a really nice help file for it. So you could say help whatever, and Dapo is scrolling down now. So you can see there's examples of how it works in the help file. It'll give you the variables that you need to make it work, and so on. Okay, and so then we get to the actual first problem. So all that stuff before was just getting it to set up. And the first thing we're going to do is calculate the thermodynamic properties of water at temperatures here. So we made an array of temperatures, 200 degrees, 300 degrees, 400 degrees, and a pressure of 200 bars. And so we can run that, and it's already been run here because this, it's already set up, but you can see. Yeah, yeah. Oh, yeah. No, fine. Yep.
Yeah. Can I?
Go ahead.
So something that will be helpful, I mean, because the file that you already have has already been run, right? So you can do something, you do clear all outputs.
Yeah.
So that as Ben is running it, you can follow along. Okay?
Yeah.
So when you do clear all outputs, you should have a clean file like this. Okay? Are we all together? Say that? Okay.
Okay. Yeah.
Okay, so I'm going to just go ahead, run from the ones that Ben had run. So again, installing PyGCC in this case, because we don't have to include the updates because it's installing over a fresh computer. So it automatically installs the latest version. Then after installation, you import PyGCC. And when you do from this, importing PyGCC means that, or importing star means that it imports every modules or every function that is embedded within PyGCC. And you can see the version. So we are currently on version 1.53. Like Ben said, all the main function that we have on PyGCC, it's listed here, and that it just helps you to be able to know what function to be able to use at any particular time. The help function is really helpful because it helps you to explain what each function does. So in this case, Ben mentioned the IAPWS95, which is the equation of state of water, the 95 edition. And when you scroll up, when you run that, hopefully everybody is able to run that. Can I get a thumbs up? Okay, awesome. So when you run that, I'm just going to go quickly. So you see what's the formulation for water, the temperature and pressure range for that, the parameters, those are the inputs.
I agree with that. There's the unit for all of these as well.
Okay. So the parameters, the inputs, Ben was saying that you do temperature, pressure, or density. So we're going to show you an example of that, but those are the parameters that you can input into that. Then the returns are the output of that particular function, right? So in terms of when you input your temperature, pressure, and you're looking at calculating your density, right? You'd see that it has density or the Gibbs energy of water, enthalpy of water, entropy of water, and all of those different thermophysical properties of water. So if you go down, there's an example in terms of usage, how to be able to use it for any particular, if you're trying to calculate on the steam saturation, on and off steam saturation curve, right? So we're going to go through an example at the bottom of that, okay? So everybody, are we still together?
Yeah, I'll point it out while we're here. We'll come back again later. Whenever you give it a temperature and then you give it temperature in quotes for the pressure, then it automatically calculates the pressure of the steam saturation curve. So that's actually, I invented that a long time ago because it's really helpful to know where that is. And it iterates on it and it can know that quite well.
Do you want to just mention the pressure?
Yeah, you can also do the same thing for pressure. So if we tell it the pressure, it'll also calculate the temperature of steam saturation as well.
Okay, so are we together up to here? Okay, so in this case, we are asking, we want to be able to calculate the water properties, and we've given it a temperature 200, 300, 400, and at 200 bars, right? So this temperature are Celsius. So when you run that on the printing output here, we are printing out the temperature. You remember I told you that we have, in this case, it's a class function, so you can do water equals to this. Then as part of that, you can put TC, which is the temperature we want to be able to see, pressure, density, rho. So it's easy. It's like you're writing your normal text. G is the Gibbs energy, entropy. When you run that, that should output exactly what the temperature that you've input, your pressure, density, right? In terms of the density that is calculated, the Gibbs free energy, entropy, right? So this is a particular case where we've input the temperature, pressure. If you go back to the case where Bear mentioned, like if you are trying to calculate that the steam saturation on the steam saturation curve, right? So I could change this to T, right? So when I change that to T, I would have to modify this because it won't get to 350.
Yeah, so because it won't get to 350, the reason he's doing that is because there's a critical point of water, right, above which water can no longer boil. So that's why 400 doesn't work, right?
So is everybody able to change that? Okay, so let's try to run that. So one thing I wanted to note is the density, right? That was calculated at 200 bars, and you can see the pressure at pressure 200 bars. But as soon as I run this, right, you see it calculates what the steam saturation pressure for those temperatures are, right? And the density. You can see that change, right?
Yeah. And so we're just putting these out so we can see them, but you can imagine making a plot like that one that I just showed in the slide. So temperature, and here's what density looks like, and here's what Gibbs free energy looks like, and so on.
Okay. Something else we can also do rather than using pressure, right, is we can specify density. So in this case, I'm specifying temperature and density, right? So in this case, I'll just say 300 kilogram per meter cube, and I want to calculate what the equivalent pressure would be, and also the properties of water at those density and as well as temperature. Is everybody with me? Okay, so let's try to run that. Oh, come on. Try this.
Pressure, the vacuum.
Yeah, I tried this density angle. Okay. So one of them wasn't working, but what I'm trying to emphasize is you can input temperature as well as density, and that will calculate the equivalent pressure as well as the Gibbs energy.
It's beyond the limits of the equation. And then we should put in an error that says don't use this, but also you know that you can't have negative pressure.
Yes.
Yeah.
Yes. Okay.
Great.
Okay. So that's for the IAPWS 95 that covers a particular temperature as well as pressure range. But when we get to a deep temperature and pressure condition, we have to go back to the deep earth model. And for that, we have this different formulation, the Zhang-Duan formulation for calculating the water properties. So again, when you run this Zhang-Duan, that gives the same breakdown that we had for the IAP-WPS, right? So you can go over that to just be able to know what the input parameters are. It's exactly the same structure as the IAP-WS. So we're just going to go down to the example here. Here we are calculating the water property at temperature of 200 degrees centigrade as well as 10,000 bar. So when you run that, this will give you the Gibbs energy as well as the density for that particular condition.
Right. And so many of you might have heard of the deep earth water model. This is what it uses to calculate, because classically the Helgeson-Kirchhoff-Flowers equation of state and all these aqueous properties stopped at 5 kilobars. And then to get to upper mantle pressures, or to work on like icy moons and so on, where the pressure might be very high. We needed to have a new formulation for that, and John Dewant did that. And now you can see like that pressure that it returned is a crazy high density, right? So it gives you a 1.2 grams per cubic centimeter, which is higher than any of us are used to for water, right? And so that's really because the pressure is so high, the density. Yeah. And so now here you can see the new pressure limits are, so it doesn't, the problem is it doesn't overlap with the IPWS very well. So the minimum pressure is a kilobar, right? And it has to go up from there. PyGCC lets you choose. So if you're making a database or doing calculations at deep earth water conditions, you have to switch to this, but it should know.
Okay. So the next thing that Ben showed was also the, okay, Chris.
I don't think so.
No.
No. Yeah.
Okay, so to be able to calculate the dielectric constant of water as well, because now that we've gotten those thermophysical properties of water, we've also implemented an in PyGCC that is able to calculate what the dielectric constant is. And with the IAP WS95, the most recommended dielectric constant formulation is the Fernandez 1997. But when we're developing PyGCC, it was developed on the back end of Sucre 92. And for Sucre 92, the Johnson and Norton formulation for dielectric constant was used. So that's why we included these two different functions so that, the user, based on an understanding of how to be able to combine this particular formulation, can choose whatever formulation they want to use.
Yeah, and I'll just point out that you might, we all try to be good students of the literature. You might think newer is always better, right? But if the thermodynamic properties, for example, the calcium ion, were derived using a different equation, then you end up with wrong answers. And that's actually, we've seen it a lot in the literature, which is actually kind of challenging because people think they're doing better, but actually they haven't gone back and done all of the work of refitting the data, which nobody wants to do because it's crazy. But that's why we put them both in there in case somebody does someday want to refit everything, or maybe teach a machine to do it or something like that.
Yeah.
But we recommend using JN91, and that's the default, right? So
Yeah.
unless you tell it to do something else, it'll use JN91.
And also the deep water model also, by the time you get to that higher pressure range, right? So we have to revert to the deep water model. So whenever you specify the deep water model, it automatically consider that when it's calculating the dielectric constant. So to be able to do that again, if you click run the help, again, shows the breakdown of the input, the output. I'm not going to go over that, but like at your time, you can go over that to see how to be able to run that. For the JN91, just to compare, in terms of how the 3D model performs, in this case, 100 Celsius, 500 bars, right, for the two JN91 as well as the Fernandez et al. 97. So when I run both, you can see how they both compare in terms of, so what you have here, it's the, what's the E again?
E is dielectric.
Okay, sorry. The E is the dielectric constant, then the rho hat.
Yeah, they're not necessary to actually know, but all this stuff goes into, or at least these ones go into the Debye-Huckel equation. So rho hat is density, but it's normalized.
Yes, it normalized density, yes.
So yeah, AH, BH, those are Debye-Huckel A and B. So one thing that we had to do if we want to make databases, we have to also be able to calculate activity coefficients at crazy temperatures and pressures. So we had to implement those as well. So those come out. Nobody ever is going to be like, oh, I've got my A now, I'm going to plot that, right? But like it actually is needed to then calculate activity coefficients. If you're going to model deep earth water, then you need to be able to do that. So that's good.
Okay. So with that also, this is the example with 3 parts, but this is at 5,000 bar. So you can see how that compares.
Great. And then we're going to go, everyone's hopefully, so you haven't actually had to code anything yet. So hopefully it's all working so far. But now we're going to do our first actual exercise. So this equation, everyone's probably seen it a million times in various forms. It's called the most useful equation in thermodynamics. I really like this. It does magic for us, right? It allows us to take energetic measurements and put them into equilibria, which then allow us to then calculate mass transfer and so on in geologic systems. So with this equation, we can calculate our Gibbs free energies of all of our aqueous species minerals and so on, and then put them together to get an equilibrium constant. Just as an example, I give the Urey reaction. This is a version of the Urey reaction. A lot of times it's written the calcium carbonate, but I've got it here so that we can emphasize the aqueous species part of it. And I also like to point out that Urey, as far as I know, is the only geochemist to actually ever get the Nobel Prize. Okay, so here we have this equation. Wollastonite, right? Pyroxene mineral plus water plus CO2 gas goes to calcium, silica, aqueous, and bicarbonate. So to do this, all right, this is classic first year thermodynamics or geochemistry class, products minus reactants, right? We get the delta G of reaction, then we can make a log K from that. So writing it out, again, we'll do this in the Python notebook, so we don't really need to go through this individually, but I really want to point out that this includes a mineral, a gas, water, and aqueous species. And each one of those has its own equation for calculating thermodynamic properties, which of course we've implemented for you, but we want to show you how to use them all. All right, so the first one is minerals and gases. So gases are assumed to be ideal. Obviously, we can use fugacity coefficients to change that, but they're assumed to be ideal. And all we do for that is an integrated form of the heat capacity equation. So for example, there are actually numerous types of heat capacity equations, but we have implemented as many as we've learned about, basically. So the one that is classically used by Supercrit 92, so is the base that we adopted here, is the Meyer and Kelly function from 1932. Since then, there's Haas-Fischer. There's several other. Berman has his own as well. Ways of basically just fitting heat capacity as a function of temperature. We have implemented them all. You will only need to think about that if you end up getting new data. Okay, but what happens is we have to load them in from a database. So here's the thermodynamic data for our wollastonite. This is actually just from a Supercrit 92 database that we've adopted and changed somewhat. So you can see here, each one is outlined accordingly. So delta G, delta H, S, V, A, B, C for the heat capacity expression, and then the temperature limit of the heat capacity fit. Okay. Right, I don't know why that's animated. So the next thing that we're going to do is the aqueous species. So calcium, bicarbonate, silica are all fit according to the Helgeson-Kirkham-Flowers equation of state. So it is theoretically based, but it's empirically fit, basically, is how the HKF works. And the important thing that they need to point out, because you're never going to learn all about HKF during this presentation, is that it has two components, one of which are species dependent, so only dependent on whether it's calcium or silica or what have you, and then one of which is dependent on water, right? So all of those need to be put together to calculate the Gibbs free energy of the aqueous species. So again, the big challenge here when we were originally coding this was getting the equation of states for water to work, so then we can calculate the thermodynamic properties for aqueous species. And this is what it looks like. The variables here, the important ones that depend on the species, C1 and C2 are basically heat capacity type variables for the aqueous species. A1, A2, A3, A4 are all pressure. So you can see they're always multiplied by a pressure term. So those are essentially volumetric properties. So like how is the water squeezing the aqueous species? Dielectric constant is epsilon there. So it shows up in this equation as well. And then everything else effectively is either constant or temperature or pressure. And this is, again, just an entry in the database, what they look like. So most of these have been tabulated. They get updated from time to time because people do new experiments or learn new things. And so they're all there. So A1, A2, A3, A4, C1, C2, omega, and Z are there. So The Helvig-Kirchhoff-Flowers equation of state is extremely powerful, so it's been extended. They call it the deep earth water model if it goes outside of the bounds towards higher pressures than this, but it's effectively the same equation. We just needed a new way of calculating density and dielectric constant. It can't work though below, I mentioned earlier, 0.35 grams per cubic centimeter, so that's the shutoff for the HKF. Or only certain species, neutral species only can be calculated in region 2 in this diagram. This is from the classic Supercrit 92 paper, and nothing can be calculated in region 3, which is near the critical point. So why is it important? Again, we can get up to 20 kilobars here, at least in this experimental study. We're calculating the solubility of quartz, and then you can see we're comparing the different versions of the dielectric constant calculation. But the other thing that the HKF permitted geochemists to do, and we've used this to great effect, is we can actually develop correlation algorithms for species so that we can predict thermodynamic properties for species for which we actually have little or very little or no data. So for example, you can see there's only one measurement on that plot on the right-hand side, but we can calculate thermodynamic properties across the entire temperature and pressure range. So if we can determine A1 through A4, C1, C2, and omega for a species, then we can calculate its thermodynamic properties over any temperature and pressure for which the HKF works. Sometimes this gets us into trouble because the data is not very good, but most of the time it's actually quite good. And the other thing that Dapo and I have done, which we will warn you profusely about, because obviously sometimes it doesn't work very well, is we allow now for you to extrapolate into those low density regions. So like above the boiling point for water or past the critical point for water. You can see in this case, the lowest pressure plotted here, 250 bars, the predictions are not very good. At higher pressures, the predictions are quite good. So the dashed lines are extrapolations. So we are fairly confident that we can predict at relatively high pressures, but very high temperatures, but not so much lower pressures. Okay, so we're going to finish this practice general example by calculating the thermodynamic properties or the equilibrium constant for this last tonight problem, Uri reaction.
Okay, so we're going to go back to the notebook. And if you're there, you see this particular session where we're calculating the equilibrium constant for the Uri reaction at 25 degrees C and 1 bar. Something to note is the equation is actually, so in case you want to modify this, it's 2. So it's 2 CO2, and that would balance the equation. So in this particular instance, as Ben mentioned, we have the mineral that we're trying to calculate what the equilibrium constant would be based on this reaction. We have a gas in that particular system. We have water, which we've done the thermodynamic properties of water, the 3 aqueous species that will be using the HKF model to be able to calculate. So all of this will go together to help us be able to calculate what the equilibrium constant would be. So you remember the thermodynamic equation, the most important equation that Ben showed about how to be able to calculate thermodynamic constant. So the equilibrium constant, so that's the equation we'll be using. To be able to do that, first we need to run this particular cell. So this cell is just to be able to refer back to those database, the SPQ21 that Ben showed earlier. So to be able to do that, many of you might not have, if you look at your script right now, right? So you might only have these two. So you might want to update that by adding this other script, because it's possible that as you copied that file that was sent to you was copied on into your my drive. So you might just want to create another line of script. So Sarah will go around in case you need help to be able to set that up. So just do content, G drive, my drive, then 2026 Goldschmidt PyGCC. So if you can do that, then you should be able to successfully run this particular line, and that will mount the Google Drive, right? So that your Google Colab can access the data within the Google Drive. Are we all good? Is everybody on that? Thumbs up?
Yeah, because it's really important because this is going to get used a lot.
No? Okay, Sarah?
Yeah,
Okay.
I'm sure I use the right app. So it's Yeah, so the sequence. Sharing pieces of the price, so you have, and it's like that, so you can check that. Yes, exactly.
And one nice thing about Colab is you can click on this directory so you can see where things are as well. Because like again, when you open Colab, it basically generates a new computer for you. And so it is worth looking there. And another thing while we're looking at this, you can also ask it to see, like you can ask Gemini to do things for you, which we're not going to do yet. And also if you have variables in your workspace, you can click and you can see what your variables are. So like as we assign things like gives for energy or whatever, they're also showing up there. So I'm a very visual person, so I kind of need to see what I have in front of me. So those are all options on Colab as well. It's bottom left here.
Yeah.
Variable. Okay. Yep.
Oh, yeah, maybe.
Check here.
Yeah, I guess so. You can take away some things.
Because it's in your drive, right?
So we should have
And then just delete the lab name. So these, sorry, Drew, is it, do you have the same copy? No, I mean, I'm going to show, I guess, if you haven't been able to figure this out, the easiest way to do this, if you just uploaded it to your drive, is to copy this line, paste it below, and then just delete the Colab notebooks part. And then that should be now directed to the folder you uploaded to your drive. Yeah. But we already.
You want that to ask you to connect to Google Drive, like, and keep some budget.
Maybe I should do this.
Okay, yeah, you just need to make sure that wherever you've uploaded it to, that is it in there? I think so.
Yeah, I should.
Yeah, find the path. So if you did upload it to some random place in your Google Drive, you gotta figure out where that is. What did it get to? If you are, the nice thing about Google Colab is that we didn't all have to install same content, but the problem is you have to get some files. Oh, you still in good.
So it doesn't work.
Yeah, so did you just upload this to how do you feel about it? Fix the board. Okay, yeah, okay. So I have to meet.
That's right.
Yeah.
You know, and there's a column. This second one, yeah, there in town, it has to repair. Yeah, it should work. It's right, yeah, right. This, over these line to line, you know, so. Yeah.
That's what should be in my graph.
Okay, is that where it is? Yeah, this is, providing.
Where it can go to your Google Drive page. Yeah, we'll put it here. This. Oh, you just uploaded that, the whole folder there, because it's got other stuff. So just drop that whole folder into that. Should do it. All right, I'm gonna keep moving forward, but we will stop in a second. And then basically, this is a very simple problem because we'll do this, and if you're still having trouble mounting the drive, we'll have to do it again next anyway, so then we can spend more time with the individuals that aren't able to do this yet. But Endapo can continue to help those of you that are working diligently to get this to work. So we're trying to calculate Gibbs free energy for this URI reaction at 25 degrees Celsius and 1 bar. So we have to set our temperature, we have to set our pressure, and I set the temperature Kelvin TK here just because we're going to need it later because delta G equals minus RT ln K. That T is in Kelvin. So I set it here just so we have it. Pressure is 1 bar. And then all of that fun stuff that we just did to get that mounted was so that we can get our thermodynamic data, which is loaded into this variable called PS. Okay, so that's what we're doing so far. Okay, so heat cap is the function we're using. So recall that I said for Gibbs free energy of gases and solids, we use the integrated form of the heat capacity equation to calculate those. We came up with the very novel term heat cap for that function. So temperature, we're setting as temperature, which we've already set above to 25 degrees. Pressure is bars, 1 bar. The species or mineral that we're working on is wollastonite. So that's in that database called PS, right? So we asked for it. Species, its name is wollastonite. So DB access dic is the dictionary where they are. And then the method for calculating that is sucrit. So that's the Meyer-Kelly formation for heat capacity. You could also use the Roby and Hemingway for formulation, or Berman. I think and Holland and Powell, I think they're in there as well. So those are all options. But here it calculates it at temperature and pressure, and then it gives us that value. Yeah.
Check that you've got the equation. Where's the equation?
So this for the heat capacity equation is hard coded in this heat capacity function.
Oh, primary heat,
The URI part.
the URI part.
Yeah, well,
Okay.
yeah, I haven't gotten there yet. Yeah.
I realized.
Yeah.
I mean, we're can switch different curve fitting, like from Berman.
Yeah.
So why just change the function there?
Yeah. You need obviously, if you're going to use a different function, if you're going to use Berman, you need to have heat capacity variables for Berman. Right.
I mean, there are different.
Yeah. So the Meyer-Kelly only has A, B, and C. A lot of the other ones have A1, A2, A3, A4. So they're actually different size variables as well. So it is kind of smart enough to figure that out, but you can break it easily as well. So yeah. Next one, we already did this, so it should be easy to do again. IPWS to calculate thermodynamic properties of water at temperature and pressure. The next one, CO2 gas. Here. So again, CO2 gas is a species in our DB access dic. So the dictionary, and it gets it out and calculates delta G now for that. Here, CO2.dg. And now the aqueous species are implemented in Helmholtz-Birkenflower's equation of state. Equation of state is incorporated in the sucrit aqueous variable here. So temperature, pressure again, but now we have to give it the name of the species that we're working on. So calcium, silicon, and bicarbonate here. So we calculate the DGs for those. And then there's the gas constant, in this case in calories per mole Kelvin, because whenever Everett Schock and Hal Helgeson did these originally, they did them in calories, and that has stuck with it. We have it so it can be converted. They are converted because like when we put tables into our papers, we like to have them in joules. So that's there as well. And now we get to the point where we want to calculate this delta G of reaction. This is what she was asking about. So calcium plus silica plus 2 times bicarbonate, those are our products, right? Minus reactants, wollastonite plus water plus CO2. And again, to the point of how do you know that you balance this correctly? You don't, right? Right. So that's, we actually have a whole nother set of functions so that it actually gives you already balanced equations, so that you can't mess this up. But here we're just doing this as an example so you can see how the code works. Log K reaction, and then we're calculating from delta G our TDA. And there's our log K minus 1.58. And so note, I put this note here because if you, like what I did to make sure that I didn't misbalance this reaction was go and compare against the database that already exists for this. This value is different than what will be in EQ36 or GWB or Freq C. And the reason is, and as I'll show in a second here, we use updated thermodynamic properties for the thermodynamic properties of silica because they were updated, but those softwares never changed, right? So they still use the old stuff, which is wrong.
Okay. So what Ben showed is a process where you have to calculate the Gibbs energy of each of those different components and then do the math yourself to be able to arrive at the Gibbs energy of reaction and calculate log K from that. There is a function within PyGCC that helps you just be able to integrate all of that together. So we're going to go over an exercise to be able to do that. So right now, just do add code, right? I know like some of you are on Jupyter Notebook, so just add another cell. But if you're on Google Colab, just do add code, right? So when we do that, first thing I want to do is I'll just go over here and copy this DB reader. Okay, so when I do this DB reader, because we want to be able to also include the reaction, right? So for our PyGCC, we have what we call source format. And that source format, we will use GWB for now. You can always use FreeQC or whatever source format. It's just that each of these software, they have a different way of formatting their particular reaction set, right? So that's why we're going to do that here. So in this particular example, I'm going to use GWB. Is everybody up to speed with me? Thumbs up? Okay, awesome. All right. So based on that, then because in our database, we don't have this particular reaction, right? So we need to be able to write it out and add it into our data, into our source database that we've just brought in. So to be able to do that, what we need to do is we do PS source dictionary. Then I'm just gonna go up and copy these guys. I know it's messed up, but I'm gonna figure it out here. Okay. So what I'm trying to say is that I need to add the reaction for wollastonite into that database, right? Will be equal to the way this is set up is also a list, and the list would be if you have a particular formula, if you have a chemical formula for that particular mineral. In this case, we can leave it empty. For this particular reaction, I have 6 minerals, but when it comes to GWB, it only includes 5. I have 6 components, but when it comes to GWB, it only includes the 5 components. So anything outside the specific mineral that we're trying to calculate the Gibbs energy for. So we're going to do something. We're going to move all this other reaction, right? Move it to the other side, so everything becomes negative. Okay, and that's what we want to be able to write here. So it's going to be 5. Okay, then we can start by writing the reactant first. So if you do the reactant, it's going to be -1. Okay, then I have water. Then -2. I'm going to convert it. So by adding that, I'm converting it to a string. So those are my reactants. Are we all together? Okay.
So it's 5 other species than will last tonight. Is where that comes from.
Yes.
Which I hate that, but that's how it is.
So we're gonna add the product. Okay. So it's gonna be 1 calcium. Okay. So what I'm trying to write, so you write the stoichiometric coefficient first before that particular species. Yes.
You like zoom in a little bit.
Oh,
We might, yeah, you could probably just do it. Yeah.
is that good? Okay. Okay. Then we had the stoichiometric coefficient for silica, then silica, then the stoichiometric coefficient for bicarbonate. Then the bicarbonate. Okay, so everybody should have this.
Yeah.
Yes.
So first here you have like a class, but does this adapt for the different places? This is connected to the other thermodynamic like database like GWB.
Yes, so
It just has to be the same.
with GWB, it's plus rather than 2+. With FreeQC, you can do 2+. There is a backend that we do the calculation because our direct access database uses plus, and to ensure that they are matching, so there's a way we do that internally. But yes, preferably just use plus. Okay. Okay, so now that we have that, right, the function that we need to be able to use is what we call calc react log k. Okay, so if you do calc react log k, our temperature that we defined, pressure, right? This species in this case, it's this guy over here. Sorry, man.
Yeah, just finish this up.
Okay, good. Then it requires DB access. So like you can see, this is as soon as you are using this particular function, it shows all the parameters that you need. So species, right? So I started by putting temperature, pressure, the species, in this case, calculating for wollastonite, then DB access disk, dictionary. So which is the one that we made by this. So it's gonna be this dictionary. Okay, then the source dictionary, it's gonna be this one. Okay. Then there is also what we call the species list. Okay, so that should be good. And I'm just gonna, because this is also a class function, and what it does, it does the calculation, and then for me to be able to request all the information I need, I would have to, then I can do, what about the calc? So each time I can do calc DG reaction, calc log K. Okay, are we still together? Okay, so if you run that, oh yeah, I know. Okay. Okay. Okay, there is a space. Hopefully there is no.
There you go.
Okay. Question?
Same number, right? Yeah.
So you don't have to go through that whole process.
Okay. So that's what we just did. And so just another example, and so we'll do this together. Minerals and rocks are rarely pure. They're almost always solid solutions. And I sent a paper to Dapo the other day that folks still haven't started using PyGCC like they could. We have implemented ways of calculating, for example, plagioclase solid solutions like anorthite 60 or something like that. Olivine, for example, FO90, smectites and illites, so clay minerals are all kinds of different chemistries. So we have this implemented. This is just a calculation for calculating solid solutions based on the Gibbs energy of mixing on certain sites within a mineral. And we can do things like this, right? So this is olivine all the way from phthalite to forsterite, and you can see the varying stability as a function of temperature in this phase diagram, for example. And then we use this Blanc et al. Method for calculating the thermodynamic properties of clay, which is based on estimating thermodynamic properties of enthalpy and entropy in two different ways. The enthalpy is calculated via this method, which I'm just showing very briefly. What it allows us to do is if you have, for example, a chemical analysis of the oxides in your sample, you can then calculate the thermodynamic properties of it. And so these are all implemented into a dictionary in PyGCC. Same thing for entropy. And so then, like, again, these are clays that we've all heard of, right? So to estimate the thermodynamic properties of these, but let's say you have got your favorite smectite, right? You can be analyzed now with a microprobe. You can also then calculate its equilibrium constant using PyGCC as well. And yeah, here's just like you can end up with these crazy minerals here and make an activity diagram for that as well. So, and yeah, the reason I just sort of rushed through that because now the next example is doing this kind of stuff again. So we're gonna open up now a second Jupyter notebook called solid solution problem.ipymb, and you'll see that I've uploaded both the completed version and the incompleted version, and you can open them side by side if you'd like, but we'll go through and help with you now. Yeah, of course.
This is the general question about the data that's getting access to the database.
Yes.
So some of them have temperature limits that currents can go beyond or space changes.
Yeah.
Is there a way to dig in and find that?
Oh,
Or
yeah.
is it flag it?
It will.
You just for that last example, you knew what the data looked like on GWP.
Yeah.
So you're able to say, well, that's wrong, that's wrong.
Yeah, you can open, so in that, you're using it actually all the time. It's called, there's a folder, so I'll just go really quickly to my Google Drive. Yeah, but it's worth talking about now. So these are installed also. So I wrote a README in here, which tells you this. But these all come with whenever you do pip install PyGCC, these come with it. But to make our lives easier today, we gave them to you as well in this folder. So the one that we're using, the default, and we'll give an example of editing this in a couple minutes here, is this speak21.dat, and it's not going to let me open that, but you can. It's a text file, so it's a ASCII text file, and you can see every thermodynamic property for every mineral, big species, and you can see their limits and so on. So they're all there. And we'll show you an example. Yeah. Yeah, I mean, we made your life easy. So like, these are, this is the stuff that I've developed for a long time that I've chosen to be my favorite, right? But that doesn't mean it's the best, right? It's just my favorite. So
Yeah.
yeah. Okay, so we're gonna work on the solid solution one. And in the interest of keeping this going, I'm gonna open the completed one. So here, solid solutions, basaltic glass. So we've adopted a new way of calculating the thermodynamic properties of glasses. And clay mineral thermodynamics are all covered here. The specific functions that we're going to use are the solid solution thermo function, calc reaction log K function, calc log K Clay's function, and then we can also give it a spreadsheet of oxide data that then are, like for example, if you analyze the glauconite, which is the example that we give here, you can use that now to calculate a log K. And then so it shouldn't be that any more people say I can't do that because I don't have thermodynamic properties for it, because actually you can calculate them now. Do you want to go through this stuff with case?
It's a folder issue. What's that? It's a folder issue.
Folder issue, yeah, always.
Okay. So again, if you're all together, let's see. Okay, so I'm just gonna clear all outputs so you can see real time as I'm running that. You can also get the same thing. So each time, especially with Google Colab, if you're on Google Colab, you have to, as you start a new notebook, you have to reinstall PyGCC. So that's why we have it in there. That it's going to install PyGCC. Then there's also this particular package called Pyrolite, and that helps to be able to work with oxide or EMP data in terms of how you can go from oxide data to elemental composition of that, how you can convert in between that. So that's a particular good package that you can use. So in this particular example, especially as we'll be working with data that is already in the spreadsheet. So if you go back to your notebook, right? So you see that there's a data. In that data, you see the spreadsheet where we have the oxide data. So if you open that, you see the way it's been arranged within that. So we have the name of the particular mineral, the EMP oxide for the values for each of these oxide that is embedded within that. So that's what we are loading into this particular notebook. Okay. So same thing that we did earlier. I'm just gonna, again, remember the issue that we had to deal with. Are you working on, can I? Okay. So when you do that, depending on where you save, so I've gone around and I noticed that depending on how you save your files, right? That's how to be able to mount and load this particular the drive, right? So you just have to ensure that it's the right name, and it's if you have subfolders, you have to include those subfolders. Okay, so I'm going to run this, and again, running this is just installing PyGCC, Pyrolite, and also some other PyGCC module that I want to be able to load alongside setting the path and all of that. So those are the things that we're doing with that particular script line.
Got 2 slashes. You didn't. Do you want to zoom in again so people can see this?
Oh, okay. Okay.
Yeah. So again, if you were running this on your own computer, you don't have to do this connected to Google Drive thing, but we were hoping to avoid like half an hour of installation for everyone today by doing this.
Okay. Is everybody able to run the first cell? No? Set? Okay, so for this particular example, also the temperature array, because we want to be able to calculate those equilibrium constant for those solid solution, right? In this particular example, these are the temperature array in terms of the temperature points that we want to be able to calculate those thermodynamic properties. So when you run that, that would show you what the temperatures are. And these are some of the functions that we have within PyGCC to be able to calculate the solid solution, right? So there's solid solution between hanotite and abite, phosphorite and phyllite. We also have the octopyroxene, clinopyroxene that does all of those, including the enstatite and ferristolite. We also have the alkaline feldspar and biotites embedded within PyGCC. So an easy way to be able to do that at first is, to see what all these other, this solid solution is, right? So we have this particular function, solid solution thermal, and in this case, we are specifying that we want to calculate at 60 degrees centigrade, pressure 100 bar, 0.7, depending on what solid solution we are trying to calculate. So for example, if we are doing AN, anatite, abite, it's going to be 60, it's going to be 70% anatite. So it's going to be AN70, right? If you specify a X, like in terms of the fraction of anatite to abite within that particular, anatite to the total PyGCCS within that. Same thing with olivine, it's going to be FO70, the enstatite, the CPX. With the CPX, the X represent the number of the amount of magnesium within the CPX. So represent the fraction of the amount of magnesium within that, and the CPX-Ca represents the fraction of calcium within that particular CPS structure. So if we run that, this generates for all solid solution type what the log K would be for the AN70, FO70, and all of these other solid solution within that. Something else that we can also print out so that you can see the structure of that solid solution is I can do, in this case, hopefully that should work. Oh, it's everything, all solid solution within PyGCC.
And it's ideal mixing model. There is excess entropy, excess gives you energy. I showed the equation extremely briefly, but yeah, it is one very specific one. Yeah.
Yes. Okay, so something to within this particular function, right? So it's calculating the log K and also calculate what we call the structure of the reaction itself. So in this particular example, I'm showing for the anatite, abite solid solution, you can see the type plagioclase, it's AN70, like I mentioned, it's 70% anatite. The chemical formula for that, molecular weight, this particular list, it's similar to what we had from our thermodynamic database, the spec 21. It just follows the same in terms of the Gibbs energy, the delta G, delta H, delta S, entropy, volume, the heat capacity coefficient, as well as the temperature. In this particular case, it's using the ash. Did you define ash? As Fisher coefficient, which compared to the Maie-Kelly, which is a 4-parameter coefficient, it's about 6-parameter coefficient. So that's why you have that particular structure. It also specifies the species, the coefficient of those species, because when we're writing the database, right, we can easily just pick those things that have been included in all of these different structures. So that's what you can see with respect to that. Okay. Clear, everyone? Okay. So when we move on to the next cell, right, so for the one I went through now, it's just to calculate all the solid solution, right? So how about if we're just interested in some particular solid solution, right? So in this particular case, I'm just interested in CPS, right? So rather than putting all, right, I could just do CPS, and within the CPS, again, has calcium within that is 1, right? And I'm calculating for a fraction of the keep forget diopside, endicovite, esthetite, all of those to be 0.85. So when I run that, based on, again, I'm not changing anything at 100 bar, 50 degrees Celsius. When you run that, you also get the log K value. So, right, remember the log K value that you're getting from that. The name in this case is diopside 85% and entoborite 15%, and the chemical formula and all of those different things that I just went over. Okay, are we on the same page? Question? Yes. It's the equilibrium constant. So it's the logarithmic scale of the equilibrium constant.
Yeah, and it's just for that specific reaction. So it's this CPX, right, which doesn't have a name anymore because it's not specifically diopside or Edinburghite or something. It's in between. And then it goes like minus 4H plus 1 Ca2 plus, like, so that's the formula or the stoichiometry of the reaction. And then the log K is for that reaction, right?
N members. Or
No, between, so it's for its dissolution
okay.
in solution, yeah.
Explain the X again, so the X is referring to the fraction of, like, for example, you have some sauces with
Yeah.
X, so it's showing that distribution.
So CPX is complicated because of those two sites
Yeah,
mixing, right? So 0.85 becomes the magnesium number, and then 1 is
Which is what it's specifying.
Yeah.
Okay, got it.
OPX, you only have to give it 0.85.
0.85, yes.
OB,
Yes.
0.85. Feldspars.
Oh, yeah.
This guy's a pain in the butt.
Yeah. Yeah, it's because of the two site mixing. So you have to specify the calcium and yes, and magnesium between. Yes. Okay. Okay, so this is using a function we call solid solution term, right, in PyGCC. The same thing can also be done with calc. You remember calc reaction log K that we just went over? We can also do the same thing. It takes the same input approach. In this case, rather than the solid solution type, right, we just put the species that we use for these the calc reaction log K, and that's the CPS, and that also exactly just outputs similar thing. Okay, so you can use the other function or use this particular function. Okay, question? Okay, so same way we've done for CPS, we can also do for olivine, right? So in this case, we're trying to calculate for olivine for at temperature condition of about 300 to 450 centigrade and couple of and 300 bar pressure. So again, using the same calc log K, we just replace the species with olivine and we specify the X, right? So the X, which is the fraction of magnesium to iron within that olivine, right? And then the temperature that we specify, the temperature range and all of those things. When you do that calculation and you run that particular code, so that should give you what the log K values for olivine FO85 would be at that particular at 300 bar with according to those particular temperature condition. Okay, question? Are we all running it together or okay? So the example that we went through CPX, olivine, right? So you can also do all the other components, biotite, alkaline feldspar, and all of those different things. So now we want to go into clay. To be able to also do for clay, in this particular example, we'll be doing the chloride, ion chloride. And this has a particular layer structure, which is about 2:1:1, and has 14 Armstrong in terms of the layer for that particular clay. And with respect to this particular clay or the inputs that the log K value will require outside, there are actually two functions as well to be able to use. So I'm going to skip this particular function, but it's pretty straightforward if you go over your code. I'm just going to refer to the same function that we're using to calculate the log K value, right? So in that particular instance, we're also specifying the temperature, pressure. In this case, the species, it's just clay, right? And it requires something we called a list called LM element, right? So this element is based on this particular structure where you have what we call the name, the fraction of silica within that particular AMP oxide analysis data that you've collected for that particular clay, the aluminum, the iron 3, iron 2, magnesium, potassium, sodium, calcium, lithium, and all of those. So you just have to ensure that they are arranged in that particular order. So when you arrange them within that particular order, again, same input file as we've done before. When you run that, that would generate the log K value for us, right? And you can see the formula as well for this particular iron chloride that we've calculated for. Okay, question? Straightforward. So you can also run the upper code. It also gives exactly the same thing. It's just that there is a particular function that is allocated to calculating the clay, right? And that is now embedded within the overall calc reaction log K that does all the reaction, right? So in that case, you just have to specify the species as clay and include the element list for the oxide analysis that you've collected, and that would just calculate the log K and the different also chemical formula for that particular reaction. Okay, so we're going to move on to the other part where we now have this oxide data in that spreadsheet, right? So you remember I showed that spreadsheet earlier, and we're trying to convert this oxide data to calculate the chemical formula for either the glass or the glauconite or clay within that particular Excel script. To be able to do that, we are going to use we're going to read the Excel, right? So again, this easily you can do or use AI, Gemini to be able to write that, but we've already included that in your script. So if you run that, hopefully you don't have any issue with the data directory that has been specified above, right? So if you run that, that will read all the particular material from that particular spreadsheet, right? So in terms of the oxide, all the different minerals within that. So the first calculation we want to do is to do for calculation for basaltic glass. To be able to do calculation for basaltic glass, so here I'm just picking up the weight, oxide weight of that particular cell for the basaltic glass, and within that cell for basaltic glass, we're also using the calc react log, and that the species is going to be glass, right? So when you specify glass, PyGCC understand, and it's just going to use the function that is associated with using glass. In this case as well, because it's glass, it's calculating the fraction of
It's a silicon number.
Is it a silicon number?
So somehow that you have oxide weight percent, but you actually don't know how the formula should look for a glass. So here you have to give it something, right? To give it a hint for what to look for.
So are you using some kind of glass model to extrapolate?
Yeah, it's pretty.
Yeah, so it's using N member. Yes, the oxide. So it's using it.
It's calculated based on the thermodynamic properties of the oxides.
Yeah. Yes. So it's calculating based.
Yeah.
Yes. Sorry? Yes, it's
like a solid solution model, I guess. Yeah. It's very simple.
It's very so it like the oxide. So for each oxide, the mineral associated to that oxide, we can maybe after we can yes, we can go over. Yes. Yeah, so it's based on that paper. Yes. Okay, so these again does the calculation for the glass solid solution. Calculate the log K for glass. As you can see, the formula for that based on the oxide analysis data that you've provided, and then the reaction, right? So in terms of what's embedded within that reaction that can then be written to your database. So all of that is generated within that. Okay, so X. No, it's just I can't. Okay, I would just give me a moment. So a good way to. Okay, so hopefully everybody is aware of the read the doc. Okay, so a good way, even for me, sometimes I have to remind myself exactly what these things does, right? So I go into okay, solid solution. Okay, so it's solid solution. Oh,
I think in this instance, it's nothing. I don't think it uses it for the classes. You're just passing it, and it does nothing with it.
okay, I'll come back to that X. Yes, it's like Ben said, it's implemented recently, so just for the workshop. So we're gonna go.
The important thing is that we did, based on that model, that Tetra model, you have to decide how many silicons are in your glass formula. And actually, there's a huge effect on the equilibrium constant. So we have it so it calculates. So there's just one silicon.
It's not needed. Yes, you're right. Yeah.
And that X was doing nothing. So yeah, exactly. You have to decide. Like we found, because we've actually now modeled the dissolution of glasses using this stuff, and it is really sensitive to that. And this works. The isolators show that this works, and that's what we picked up.
So the X doesn't, the reason why I think I copied that X was because I was copying from the solid solution. So you just copied over. So you don't need the X. What you just need is just the oxide weight. Once you put the oxide weight, it does the calculation generates the thermodynamic properties for you. So that's what I just did. I took out the X. It's not needed somehow. I need to tell myself that. Okay. Okay. So when it comes to glauconite or any other clay that you have, again, we have the oxide. So we have those oxide in the glass that we went through. We needed those oxide because the glass log K was based on calculating the log K of those oxide, the mineral component of those oxide, and doing a solid solution calculation based on that. But when it comes to the clay component, we need to now transform those oxide into the element, right? So that's why we use the parallite, and parallite does the mineral transformation, the transformation of those components. So if you run that, we're going from, so if I go back up, right, you see we have this oxide content fraction to now redistributing those composition of those oxides to the element, right? And based on this, now we can then input this into calculating our log K value for those clay minerals. Something to also keep in mind is that in PyGCC, there is a charge balance component that needs to be ensured, right? So that charge balance that we try to do, depending on the layer of the clay, right? So in PyGCC, we have 7A, 7 Armstrong, we have 14 Armstrong, and we have 21 Armstrong, right? So each of those layer, their charge balance, they have to add up to a particular number. In this particular example, this is for the 14 Armstrong, right? So if you don't have to do all those charge balance, it's done within PyGCC, but sometimes PyGCC will give you error if it's not charge balance and you want to do it yourself. So that's why we included a code here that just helps us just be able to check that for all those minerals that we've included in the spreadsheet, there's a charge balance that adds up to 22, because for 14 Armstrong, they have to add up to 22. Okay, then the log K for that, again, using that calc react log, you have to specify the species, clay, and the elements based on the elemental transformation that we've done from those oxides, right? And then when we do that, so here's just a script that just shows that. And in this case, we're just showing you what the silica content for each of those particular clay or different glauconite that you have within that. And you can calculate the log K value for that. I don't know why. Shouldn't. Okay. So what you can see here, it's the log K value at, because again, remember we had that temperature range, right? So this is we're just showing at 60, at 0 degree, at 60, it's actually 0.01 because internally it does the calculation of at a temperature higher than 0. Then at 150 degree, this is what the log K value that we've calculated for that. Here is just to show the differences between the log K and the Gibbs energy, or for the different clay mineral and their log K at the different temperature condition. Okay.
And so that. So the next thing that we're going to do is now we know how to calculate the thermodynamic properties of individual species. But let's say something new, you get the new issue of GCA in your email, and it says, oh, I've got new thermodynamic property for the rare earth elements or something like that, and you'd like to put those in your database. That's the next example we're going to do, is how to do that. And again, the example that I already gave is that we've in PyGCC have hardwired so that we always have updated silica thermodynamic data, unless you opt to use the old stuff for whatever reason. And so that's already happening, but we're going to show you how you can do this for other things as well. Again, the first principle is that you must not fool yourself, and you are the easiest person to fool. That's a classic Feynman quote, and I think we all fool ourselves into believing various things because it's easier to do that than to do the hard work of changing it. But we actually have made the hard work easy for you. Okay, so probably everyone knows this, but like if you wanted, for example, to derive the Gibbs free energy of an aqueous species like calcium or silica, you have to do it based on some kind of experiment, right? There's no way that you can put, your silica aqueous molecule into a calorimeter and get its enthalpy. You have to do this usually determined by solubility experiments or speciation experiments. So for example, and this is the example I'm going to give, but it's kind of a trite one. Quartz going to silica aqueous at K25. So all you have to do in these experiments at any temperature is just measure the silica concentration, and that's the log K of the reaction, because the only thing on the right-hand side of the reaction is silica. So you're measuring its activity or concentration directly, and then this guy's activity is 1. So when we write the log K for this reaction, looks like that, product minus reactants. So in this case, again, if we know Gibbs free energy of quartz based on calorimetry measurements, and we do, right, because that's a fairly general, you can measure the log K at any given temperature and pressure, and from that you can get your Gibbs free energy of silica, right? So if you know this value, if you know quartz, and you know this, because this is your log K, then you can calculate silica aqueous, right? And so that's what is done, right? So that's how thermodynamic data comes to be, right? If we have measurements of quartz solubility, in this case, quartz solubility is measured across a whole range of temperatures and pressures, and we know quartz thermodynamic property across all of those temperatures and pressures, and therefore we can calculate delta G of SiO2 aqueous across all those temperatures and pressures. And then we can use the Helgus and Kirkham-Flowers equation regression tools to get those A1, A2, A3, A4, C1, C2, delta G, and so on. Unfortunately, the nature of thermodynamic data is that the properties of one species depend in many ways on those of another species, right? So SiO2 aqueous is a beautiful example, right? So SiO2 aqueous then goes into all of the reactions that we were just writing for the plagioclases, olivine, etc. All of those are based on the thermodynamic properties of SiO2 aqueous. So there are 180 reactions, more than that probably, depending on count a different way, that include SiO2 aqueous in the GWB thermo.tdat database. So our calculation, for example, of the solubility of magnesia and olivine, forced to write, depends on our thermodynamic properties for silica, right? It also depends on the thermodynamic properties of magnesium and H+. H+ is a freebie, it's 0, but also water as well. So it explicitly depends on how we know solubility of quartz and how that goes into our regression of our thermodynamic properties. And then Don Rimstead in the 90s came out with this paper. So he did these experiments, kind of crafty. All he did was, put some quartz into a vessel and let it sit for many years. And Jim Palandri famously said, rarely does so very much hinge upon so very little. So what Rimstead showed is that actually quartz has a different solubility at 25 degrees Celsius than was used originally to regress the thermodynamic properties of SiO2 aqueous. So he did these experiments for 13 and a half years and showed quartz is actually, again, this is in his, right up 80% more soluble than was used in the derivation of thermodynamic properties. And so what that means is that we are using the wrong Gibbs free energy for silica, and therefore anything that we try to do at low temperatures where we're modeling the dissolution of a silicate mineral is incorrect, right? And it's easy to just change that, but you can imagine before PyGCC and its predecessor, which was called dbcreate, it was an onerous process to write 180 reactions and do all these calculations again, especially if you're going to model at different temperatures and pressures. So GWB still ships with that old data, right? And so does Freaksy. All of these, they all ship with the old data because it's a pain in the butt to make new ones. Right? So all the log games are systematically offset. So what do? Right? We just put a new one in our database and make a new database. So that's the example that we're going to do now, is how to make a new database. And I gave that silica example, but again, that's hardwired in. So what the DAPO is going to show example actually with these rare earths instead. Yeah, take it away.
Okay, so if you can go back to your notebooks, because of our time, just if you can open the one that has the suffix completed so that we can run through that together.
Database, right?
Yes, so this particular one. Okay. Okay, sounds good. So similarly, let's do clear all output so that we can run that real time and see what we are generating when it comes to result. Okay, something else I also want to mention is, remember this part, right? So you want to, if you can go back to your old script, one of the scripts that we've worked on, so that you can ensure that there is no error when it comes to that. So in my own case, the file that we'll be using is directly copied on my drive, right? So I have the file, the folder name as this. Oh. Okay, so you should have, based on what you've worked on in the past, right, you should have a particular directory that you need to be able to refer to. So in my case, I think over there you have to do subfolder and ensure, just copy from what we've done in the past, okay? Are we all on the same page? Thumbs up, we are all on the same page? Okay, Seth, do you want to go around just to ensure? Drew? Okay. Okay, so this particular example, again, when you go back to the folder that we've shared with you in terms of data, we have this CSV file called mineral data. And that CSV file, what it does is that there are some species that we don't currently have on our database, right? And this particular example is a rare earth element. And here you can see DYEU, and all of that, they've been formatted in such a way that, we have for their aqueous species, we have their Gibbs delta G, standard Gibbs free energy, the standard entropy, and CP, and all of those different parameters that we need for the HKF model, right, that Ben just went over. So we have those in the spreadsheet. And what we want to do with that is to find a way to see how we can load them into PyGCC. The other component is also that our database is missing a sulfate mineral, in this case, gypsum, right? And to be able to do that, to find what the thermodynamic properties of gypsum is, right? There is a book called Let me find out if I can see. So there is a collection that Robbie and Emway. So there is this collection that has so many minerals, aqueous species that have been collected over time that are not also included in our current database, because our current database is coming from my Kelly formulation. So, and that's based of Sucrit 92, whereas for the Robin Emway database is based of Ash Fisher formulation. So right now we're still working on how we're able to also internally create a dictionary that, or find a way to extract all the data from this particular database so that it exists somewhere that the user can always refer to. But right now we don't have that. So this is also another source for you to be able to collect some of the thermodynamic properties for any missing minerals. So in this particular case, we're going to use that for gypsum. Okay. So if you're doing, again, same process, it's a new notebook. So we have to ensure that we install PyGCC, right? So if you run that with me, that should quickly just install PyGCC. Then from installation of PyGCC, we are importing this particular or every module that is embedded within PyGCC. So if I go to the CSV data that I just showed in terms of mineral, you can see it shows or listed all the component of that is associated with the HKF parameter in terms of the A1 to A4, the C1 to C2, and the omega, the bond coefficient that is associated with that. Again, let's mount our Google Drive for those that are using Google Colab. If you're running that on your on Jupyter Notebook on your computer, you don't have to do that, right? You can just refer to the particular directory within your computer. This I mentioned earlier, just to ensure that you copied it over from the previous notebook that we worked with, and that just generate or make sure we are referring to the right directory. So for the read CSV, right, the directory that we've where the data is currently listed and the particular CSV that we want to load. So when you load that, that just lists all the all the rare elements, species, and all of those different thermodynamic properties that is associated with that. So yeah, it's just us trying to, I don't know why it's repeated twice. Sorry about that. Okay. Okay, so I'm going to go straight to part two. Again, you can take your time to look over the part one in terms of, these are just checking all the data or all the parameter that is associated with that. If we go to part two, so we have a source database, right? In this case, we are using thermo.2021 from GWB. And when we load that, what we want to be able to see when we load that is we want to compare. Sorry, Ben. Okay. Okay. So going back to the part two, when you run this cell, right, it just shows the source database that has been loaded into Python that PyGCC will now use in generating the database that we needed to generate. Also, the temperature component, the temperature list, right, has also been listed here. Then if you go next, you see when you load that particular database with respect to also loading the thermodynamic properties database as well, PyGCC creates categories, and based on those categories, you have the elements. Each of those geochemical code formatting. They have their way of doing those categorization, elements, basis species, redox, aqueous. The array of elements data that we'll be using here is going to the aqueous category of this particular code, right? And based on that, we can see, for example, here is just to show how many of these new species, right, that already exist within our source database. So here we are showing those that are not present, right? So you can see that we have 22, right? We have 22 that we started with in terms of how many rare of element species that we have. Then when we compare that with what we have existing within this particular database that we are using, we see that we have almost, let's see, we have almost 12 or so that are missing, right? So we want to be able to add those 12. So to be able to add those 12, what we need to do is first, we use this particular code to be able to write the thermodynamic database for our existing. So for our existing thermodynamic, the source database, as well as the thermodynamic properties database, and to be able to write any database for this particular example, we are using GWP format here, right? So again, the input temperature, pressure, which is a same saturation curve, right? The data set source format, which is GWB that we've already declared above. Solid solution, whenever you use the word solid solution equals to true, it generates just solid solution for all the different like PyGeoChemCalc, olivine, as well as CPS, just generate all solid solution that we've in default added. Like it goes from, say, for example, 0 AN 0, which will be AB, right? Abertite, N member abertite to anortite N member, right? So generate every 10 fraction solid solution within that. Same thing it does for CPX. Clay thermo also generates some specific thermodynamic for some clay minerals that just automatically is generated within your database. You can also, outside that, you can generate any other clay database. The density extrapolation, you haven't specified that. Okay, so the density extrapolation, Ben is going to go over the theory. He mentioned that, but he's going to go over that. So I'm going to skip explaining that for now. So when you run that, that would generate the database, and this line is just to check that the database that we generated, either it exists or not. So you can see it would, after running that, it would show this particular instruction that a new database has been generated, and these are the formulation that I had used, in this case, JN91, right? So because default, we are using JN91. If you wanted to use another formulation for dielectric constant, you can specify that particular dielectric constant into. So if I go here, right, you can see dielectric method, right? I can specify if I want Fernandez 97 or the deep earth model, right? So you can always make all of those changes within that. So the question is, when you look at this, where does this generate your database, right? So if you on Google Colab, right, you can go to files, it will generate a folder called output. So if you see the folder outputs, depending on the source format that you've requested, if it's GWB, EQ36, FreeQC, pFlowtran, TOF-React, to create a folder for that particular geochemical code, right? And it will generate two different files within that. One file is the newly generated database, and the second file is what we call the species not found text file. So if you open that, let's see. So what this does is, based on your source database and the thermodynamic properties database, is trying to match, right? So someone asked earlier if you have calcium, and we write that calcium as C2 plus rather than C plus plus, because in PyGCC or in the database, thermodynamic database that we had, it's written all the cations are written in terms of fully expressing the plus sign rather than 2+. So if it's not well correlated, it's going to send it out as, oh, this is a species that is not found, right? So those are the list of species that are not found. And also within this, there are also some thermodynamic properties that we don't have in that particular, or in the particular database that we've used. So those are the ones that it has been listed here, and you can go over them just to be sure that it has not excluded the particular species, component, mineral, gas, or anything that you're interested in, right? So that's a good way to be able to check that.
So I'll just mention right now. So the thing that everyone was struggling with before, because it's a pain in the butt, is like balancing reactions, right? And the crafty thing that we've done here is they're already balanced in the database that you've started with, right? So we just strip out the entire reaction from the database, and that's why it can so rapidly generate a new database, is we just take the reactions directly out and then put them in. And it's still beta, but like we can technically go from a GWB database to a FreakC database or whatever. So if you like your database that you use and you made, you can translate it as well.
So yeah, to be able to do that, so you remember I told you like the source format, right? So the source is like, hey, my source format I'm using, it's GWB. You can then use that as the source format, and then the data set that you want to generate is going to be a FreeQC data set. So you can specify, in this case, I'm saying my data set is same as source format, right? But if I want to go from GWB to FreeQC, I would have to specify my source format to be GWB, my data set to be FreeQC, and vice versa, the same way. Okay, so the example that I just went through right now, it's just to be able to generate database, GWB database. So now we still have those array of element data that we've not incorporated, right? So this is what we want to be able to do. To be able to do that, what we want to do is that we have those spreadsheets for those rare elements, right? We now want to map those spreadsheets into our existing thermodynamic data properties database, right? And save that so that for any subsequent database generation that we want to be able to make, we can always refer back to what the modified thermodynamic properties database that we've generated. To be able to do that, right, here is just saying, I'm reading from this particular CSV files, those new database for array of elements, and I want to create this particular new database, that thermodynamic properties database that I want to continue to refer to. So if you run that for exercise 6, right, that shows that new database has been generated. And this DB access, right, DB access modifier, it's a function within PyGCC. And what that function does is that it just look at the spreadsheets, right, in terms of how all the arrangement of these different properties, and just add that to the thermodynamic properties database that we have, that comes usually with your installation of PyGCC or any particular database that you want to be able to refer to if you want to use your own database. So that's that now generates this new this, right? So if you go here, right, after running that, you should be able to see that this new database has been added, right? So we can quickly open that and see. So I'll just jump to, because the database is also written where you go from minerals that goes to phase transformation or down to different species. So the aqueous species, it's over here. So for example, if I look for, okay, yes.
I think what you're saying is that you put reactions into the database that are reactive formation reactions and phase transformation reactions, and you recalculate it to account for those small steps.
Yeah.
Is that what you're saying? And why do you need to go through this whole exercise when you report your data?
So we're conflating things because it's actually it's so intuitive to us that we probably are doing a terrible job of explaining it. So there's really two separate databases, right? One is the one that you can actually use for modeling, right? Has reactions, dissolution reactions, like the Geochemist Workbench database, for example, will have gypsum goes to calcium plus sulfate plus H2O, right? Do you want to open
Yes.
just one of these databases to see what they look like?
Okay.
I used to use ones that just have the basic information stuff, like rotors.
Yeah, and so then right, so
I can't.
but you can't use that unless you're using a Gibbs energy minimization code, which we're not.
So
Then you can't use that directly. You need to calculate. Yeah. Then you need to calculate log case. Again, it won't open DAT files for reasons I don't understand.
Okay, sorry, I'm doing it the other way around, calculate. Gibbs free.
Yeah, and so we are doing that, but we have to calculate Gibbs free energy for all of the individual species, right? So for calcium, for H2O, what is that?
Right. So we're doing the same thing, who's doing it in your database, whereas.
Can I open your text box?
Yeah.
Like, can you open it in text?
Yeah,
Text.
sure.
The two databases. So that
What did you just do? Okay, let's just open that there. So this speak21.dat is, I've showed in the slides a little bit this. So this is, if we go down, like this was originally made for sucrose, right? So chrysotile, for example, here, delta G, delta H, S, B, A, B, C, right? And those are all there so that then we can take them and write a balanced reaction between that and magnesium and silicon and H plus. Then at whatever temperature and pressure we have to calculate the thermodynamic properties, delta G's, really, for all of those species and the minerals and gases at every temperature and pressure that we want to make our new database at. And then with our new database, if Davo can open it. So now you can see there, this is now formatted for GWB. So all that stuff is just headspace. So then like, these are the basis species. So they're not log Ks yet, but if we go down below that, to acetic acid, for example. Now you have this balanced reaction, and now we have 8 equilibrium constants. And so if we want to calculate acetic acid dissociation at 300 degrees, that's how we do it. Right? And so the thing is, like and I still review papers all the time where you see this, people say like, I can't model that, it's outside of the limits of my database, but actually it's not, right? Like we can easily calculate a new data set. We just did it, it took like 3 seconds. A new data set at 500 degrees or whatever you're modeling. So that's kind of the utility here. And this is what we originally wrote it for, but then all this other stuff came by.
Sorry, can I ask what kind of Gibbs energy minimization accuracy?
We do not do that. I just mentioned it because if you're not going to do Gibbs energy minimization, you have to do speciation, right? And so this is PyGC is a speciation code, GWB, EQ36 are all speciation codes. So unless you're going to use the Gibbs energy minimization, which is then you can use Gibbs free energies without calculating equilibrium constants. Otherwise, you have to do this to get speciation. So what we're doing, what this code does is it strips all of these reactions out, it gets them balanced, and then calculates them again.
But I mean, sometimes the experiments only they've done are very integrated that you're then extrapolating.
Yeah, I mean the whole HKF is built. I mean it is, but the whole Helgeson, I mean he's dead now, but the whole idea was like we can predict anything anywhere, right? That was the whole idea of the HKF, and sometimes it's bad, right?
Yeah.
But somebody has to do the experiment to prove it's bad. Yeah. Until then, that's the best we have, right? Yeah. Yeah.
Okay. So hopefully that's clear. When I'm referring to thermodynamic properties database, I'm referring to Speak 21, right? I don't know, because we are familiar with it, so I don't want to be using Speak 21, but whenever I'm referring to thermodynamic properties database, it's those database that has the thermodynamic Gibbs energy, enthalpy, entropy, and all of those things. And the other, which we refer to as source database, is depending on the format, right? It could be free QC, and that basically is just to write the reaction, the log K, and we are stripping off the reaction, the balanced reaction, and using that to calculate based on which species, mineral, gas, all of those different species, water, calculating the log K, and then rewriting the database that would then be utilized for free QC, GWB, and any of the other geochemical codes that you need. Yes.
Well, we'll talk about Driesner.
Yeah. We'll talk about quartz geothermometer and
But in
which
terms of
would be-
like activity coefficients, like the Pitzer model and stuff like that, we can do it, but it's not us that's doing that because that's actually, we don't derive those parameters. We just reuse the ones that already exist.
So in our database, we copy them over. If you have a source database that have pizza, we copy them over. We don't do any calculation. I think we've talked about at some point how we can get into now doing those recalculation. That would be something that will probably yeah. Okay. 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 So if you go into here of, unfortunately, I can't find it. Okay, so I'm just gonna try to, or if you can find it, if you can download, I would recommend that you download, and you just compare, because this was the one that we were using, right? And now we've added the new array of elements database into that, right? So if you save that, and let's try to open that, and what we can see, I think I have an example that I just copied. Okay, so this is now my new database, thermodynamic properties database, right? And if I compare that with this, right, I don't have that, right? It's missing. So that means that we've now generated a new database that now has those thermodynamic properties that we have in that spreadsheet, right? And we can utilize this for further database generation. Okay, is that clear? Okay. Okay, so now with that, okay. So we can run this. This is just to show that the database that we've generated exists within the particular folder that we're going to be referring to be able to generate a new database, right? So yeah, it's also just to verify that all the array of elements is now within this new database, right? So again, it's referring back to this new database that has been generated and just checking to see that it's all included within that. Then now that it's included within that, we can then use that to be able to calculate or generate a new database that we can use for our geochemical codes. Okay. So with that, we can also move into adding a new mineral in this. So the example that we went over is just adding aqueous species, right? That we have within that. So this example of new mineral that we want to add within that, like, is going to be using our Fisher its capacity model compared to the other one that I use my Kali model, and this is about a 5-parameter model, its capacity model, compared to the 4-parameter its capacity model that we had within that. So here is just a way that we've created in PyGCC to help you understand how you'll be able to, list that. So it goes from, we defining the Gibbs energy, entropy, V, or the heat capacity coefficient that is associated with that. The same way, remember when we were defining the PS source dictionary, we can also do the DB access, right? So there is DB access, there is source, right? So hopefully it's not conflicting. So the DB access, now it's just how, based on this database, right? Data that we've collected from Robbie and Amway that I just showed over here, that data. Based on that, now we can then use that because that data is collected or written, collated in joules, right? Joules per moles. In PyGCC, we do the calculation in calorie per moles, right? So we do that conversion. This is what we do in that particular conversion over here. And then based on that, when you run that, right, be able to see that now we've converted all those parameter to calorie per mole, and that parameter can then be incorporated into PyGCC to be able to calculate the thermodynamic equilibrium constant for gypsum and include that in our database. Okay, so this is the reaction that we are looking at for gypsum, right? Calcium sulfate with 2H2O within that. Same process that we did. Again, our source database, again, where all the reaction is, does not include gypsum, right? So we have to define that. Remember the example we went over, just generating that. So in this case, the first thing is to define that 3 components. Again, the question was asked about 3 components because in GWB, it excludes the specific mineral component that you're trying to calculate the equilibrium constant for. So that's why it's all the other minerals, right? So 3 components, the stoichiometric coefficient for that with the different components that is associated with that. Something I also mentioned earlier, hopefully, it's that there is a categorization that is done when PyGCC reads all of these database, the source database. That categorization is elements, bases, redox, aqueous, electron, minerals, gases, oxide. When you are writing a new mineral, right, that PyGCC does not understand what category. There is no way, hopefully we can get into that, but for now, there is no way to be able to understand that this component you're adding is a mineral or is aqueous or is gas, right? So that's why based on this, so you can see this is labeled 0 to end, right? So 0, 1, 2, 3, 4, 5, 6. So that's why when you see 5 over here, when you see 5 over here, that was an attempt to be able to add gypsum to the mineral category. The reason why we are doing that is that, you remember our calc reaction log requires that he understands that it's a mineral, it's a gas, because if it's a mineral and gas, it uses the same equation of state. If it's water, it uses the water equation of state. If it is aqueous species, it uses the HKF equation of state. So that's why we need to be able to add it to the appropriate category so that it can understand what kind of mineral that would be. So when you do that, right, that list or that adds gypsum to the mineral list. And when you, this is just an attempt to be able to see that does gypsum now exist in that mineral list? Yes, it is true. Do we have gypsum in the source disk? Right now, it is true. So that means that we can then do our thermodynamic calculation or equilibrium constant calculation for gypsum within that. So based on that, again, using that calc reaction log K, so everything is embedded within that just so that it's easy. You don't have to be dealing with so many functions to be able to do your calculation. Same thing that we've done in this case, same thing that we've done for solid solution, the species, right, is just going to be gypsum, right? It's very case sensitive, so you have to ensure that whatever you're specifying here, right, it's exactly what PyGCC would take. So in this case, when you run this particular code, right, that would then calculate the log K. Let's see. That will calculate the log K. So if I do that, I can output the log K while calculating that. Okay, so this is the log K at a different temperature, right, range that we specify, and at 50 bar. Okay, so you can see that I've added log K to here because the calc reaction log K, right, requires or takes 2 functions, right, either as an output, the log K or the reaction, everything that is embedded within that reaction. So here is just a particular structure. We call it like a formatting structure to be able to see how we can then write all the data that we've generated within that to either a free QC, a GWB, a pFlowtran, or any of the geochemical code that we need, right? So when you do that, where is it? Okay. So I'm going to run that. When I run that, there is this particular function, right? So this is an attempt where, because we can't write it to the newly generated database, right? So we output it to a text a text file, and the text file, in this case, we specify what the source format of that text file would look like in terms of the data set that we need, GWB, with the log K that we calculated from previous cell, the reactions cell or dictionary that we now generated. All of that is now being output into this gypsum log K text. So if you go here, you'd see it generates a new file called gypsum log K value. If I open that, you see it's formatted in a GWB format. So what it does is gypsum, the formula, the molar volume, molecular weight, the number of species within that reaction, the reaction, right, and their coefficients, the different species, as well as the log K value. So to be able to utilize this in my newly generated database, right, what I just need to do is now go back into the database that has been generated within GWB, right? So if I download that, I don't know the folder. Okay.
Just want to open it.
Okay, so this is the new database that I'm going to use for my calculation, right? Then the gypsum one that I just did as well. So if I download that, okay, so what I just need to do is just to copy this over into this. Again, because don't forget the different category, right? So they go from elements, bases, redox, aqueous, mineral, gases, right? So you have to ensure that you find the particular category where the minerals are. So in this case, you see, this is a mineral category, or a good way to do it is just find minerals, right? So it shows you how many minerals are in. This is a GWB particular format. You can just copy that and just save. So anytime you open the GWB, the new mineral is already embedded within that, and you can use that for your thermodynamic calculation. If it's free QC, same approach. P-Flowtran, same approach. Every other geochemical code that you're using, it's going to be the same approach. Question?
So you'll see it more abundantly in a second here, but very perceptive people in the audience might have noticed that these all look kind of okay, and then there's one insane log K here. Does anyone have any idea what's happening?
Is the gypsum?
No, that's not. The code is agnostic about that, unfortunately. So if you go back, well, yeah. So temperature, and I guess we can look at the variables. So,
Yeah, you can out CT.
let's look at this here. So the temperature that we put in goes up to 350 degrees, and it's off. You see, so way up above, we went from 0.01 degrees to 350 degrees. But then we said we want all these log Ks to be calculated at 50 bars. 350 degrees and 50 bars is vapor for sure, right? So it's calculating. I showed you those density extrapolations. It's calculating you a log K, but it is not like that is not a reasonable log K, right? So that's what it's doing. And yeah, the next exercise, I think we'll get into this in a bit more detail.
Okay. So again, the density, if you take out the density extrapolation, right? Because that data, so Ben, do you want to expand? Like,
yeah, and then so if you say don't use the density extrapolation, now the code knows that 350 degrees and 50 bars is bonkers, right? And you shouldn't go there. It gives you not a number, right? Instead, and it doesn't, like you might have noticed before, it was like really working hard to get it, because when we do density extrapolation, we actually calculated 5 log Ks and then we extrapolate into the vapor. And so it has to do a lot more work to do that. And like you can tell right away that the number it got is crazy, right? 350 degrees. And then it was like in the 500 range, which is a bonkers number.
Increase the code once more that I can see.
Yeah, can you zoom back in?
Oh.
Sorry, I zoomed out to find variables.
So when did you change this?
So
Yeah, okay, density extrapolation.
Yeah, so if you change it to false, then that should work. Okay.
yeah,
I think it's
Means that the extrapolating behind temperatures actually never works.
oh, it works. I showed you it kind of works in some places, right? But 50 bars and 350 degrees is like an implausible geologic condition, right? It's like your stove kind of thing, pressure cooker.
okay. So I know going back to the source format, like I said, this is a GWB source format, right? So if you want, we can also do free QC, right? So you can change this to free QC. So if you do change that to free QC,
It has a NAND in it. Doesn't like the NAND.
oh, yes, okay, sorry. I'm gonna go back to the okay, so this is a free QC format. You can see. Okay, so I can change that to EQ36. Yeah, because I need it's okay. Tough React. I need something that this guy needs for frequency. So this is what the tough React format will look like. pflowtran. Same thing we can also do for crunch flow. Okay, so you can easily just do any particular format that you need your geochemical bench to be. Okay, so now going back to the rare element, right? Where we've now used the DB access, the newly DB access that we've generated, and we now want to include that in our new database, right? So rather than referring to the default DB access, which is the original one, we can refer to the newly modified one, right? So when you so here is just the line that now redirects PyGCC to that particular modified direct access database. So when you run that, then you can see, you can compare what the result will look like. And you'd see that when you compare that, you'd see that in this new database, you have those rare elements that was missing in the previous database that we generated without those rare elements. Let's see. So also the size, you can see like there's a difference in the size, but within that, if you run this, now within this new database that we've generated, we can now find all these aqueous species for those rare elements.
Great. And so you've seen now how long it takes to make a database. If you find that it's taking way longer than that, it's probably because it's doing density extrapolations and they're crazy. And so automatically I had turned this off when we were making this new database here. So I said density extrapolation, no, but if I had said yes, then it would take a really long time because it has to calculate basically an entire another database worth of equilibrium constants to do that. So we want to just show off some of the other capabilities of PyGCC because these are things that we've added through work that we were doing. So in this case, it was with Drew Severson here that people have been for a long time estimating the temperature and the pressure of the reaction zone, the so-called reaction zone, or the place of last equilibration in the subsea floor at mid-ocean ridges. Obviously, these geothermometers can be used in other places as well, including, in continental hydrothermal systems, as long as they're equilibrating with quartz on the upflow. So yeah, the idea here is that somewhere deep in the subsea floor is the so-called reaction zone, and then we get our vent fluid that is derived from that. And so the chlorinity tells us about reaction zone conditions. What happens is that because it's a saline fluid and it's not pure water, you can actually separate phases, right? So you can actually have a vapor and a brine, and the vapor is most often what we use for these types of techniques. So that's salinity lower than the salinity of seawater that comes out of the system. You can see most vent fluids look like they've undergone phase separation and are on the vapor side of this curve. So what we can do is I've already shown this before, but we can take our quartz equilibria, so silica activity, to calculate, we can calculate it based on the silica that we made in our fluid, and we can derive from that a temperature of reaction. And from the salinity, because whenever phases separate, we can have a plausible pressure and temperature of that, where it achieved that chlorinity, right? Whenever it has undergone boiling, we can use those two tools to actually get the temperature and pressure of last equilibration, or the so-called reaction zone. So we're going to give an example again of how to use PyGCC to calculate pressure of reaction based on vent fluid chemistry. But what you should take away from this is not just this is what these guys do to calculate temperatures and pressures in mid-ocean ridge hydrothermal fluids, but also that we have implemented this Driesner and Heinrich equation of state for saline fluids that actually has huge applications across the geosciences. So to do this one, we are going to open up another file. We got to get to it. Back in our notebooks folder, and in this case, it's the geothermometer one.
Okay, just make sure you open the completed one again. So that way, something to also note is that we'll be referring to those databases, so you might want to just go quickly down and ensure you modify this, right? Again, depending on where your directory is, the path, so just modify that or include that. You want me to zoom in? Oh, sorry. Okay, is everybody with me? No? Okay, so if you go down or just search, if you do Control F, you should be able to search where it says path, lib, and that should take you to that cell where you need to modify and just ensure that you're referring to the same path, right? So that when we run this, it's okay. So everybody's good? Okay, all right. Okay, so in this particular example, right, we have an hydrothermal vent fluid. We have measured that. We have the chlorinity level to be 0.757 moles per kilogram solution, right? And we have the silica in the solution to be about 7 millimole. And what we're trying to do is that we want to be able to calculate where the reaction zone temperature or depth, right? The reaction zone temperature pressure, right? So we have the chlorine geobarometer, right? And the silica geothermometer, and we're just trying to find a cross section where they both intersect, and based on that intersection, we use that to be able to calculate or understand the temperature and pressure of that intersection would give us where the reaction zone, or where the two fluid, where they intersect. So again, these are so same way we are the equation of state for water. We've also included the Driesner equation that also included the salinity of water. Based on that salinity of water, that helps us be able to see or track where the critical point of water would change, right, as you increase the salinity of water within that. So the function to be able to do that, right, that we'll be utilizing for this is what we call the Driesner NaCl. We have the equation of state and the IOP IEP WS95 for water, and we have all of these different functions that now hopefully you're familiar with to be able to use. Here is just some modules to be able to do some conversion in between, right? Because when you go from molarity to fraction or to molar to weight fraction, we'll be utilizing that a lot, right? So this is just a good, easy function that we've generated to be able to do that conversion. Also for when you have your silica in NaCl solution as well, we have this particular conversion as well that we've incorporated. So same way, we can just start by, clearing all outputs and ensuring that we are running this real time. So let's see, as with any, okay. So many of you might have the same error. It's because we've opened so many Google Colab. So let's try to close the ones that we've done in the past. So just find ones to close. Okay. Okay.
And go manage the station and then I can close all the others.
Yes.
Click on manage sessions.
Oh, really?
Just click on up and then you just shut them down.
And then close all the others.
Okay. Again, if you're running this on your local machine, you don't have to go through, closing session or reinstalling PyGCC. Once you install it, it's in there. The only thing you need to be aware of is that subsequently, because we continue to update PyGCC, just always ensure that you update to the latest version of PyGCC. So again, these are just explaining the Dirichlet function, the equation of state for saline water that we've included. Same way, you can just do temperature, pressure, right? In this particular instance as well, you can do temperature, pressure, only that you also have to specify the fraction, right, of NaCl within that particular solution. And either you have your molality of NaCl, you can convert that molality to the fraction of NaCl, or you can go in between. That's why we have the previous, some of these functions that you have within here, where you can go from molality to fraction, and that can just be easily something that you can call or input into this particular function. How do you calculate viscosity? You mean for the saline water or for water itself?
It's Dirichlet and Heinrich have all of these. They're all incorporated in Dirichlet and Heinrich equation.
Yes. Okay, so in this particular case, right, we're trying to find, to calculate the brine properties at 200 degrees C, 500 bars, right? So in this particular case, we have 0.5 molar NaCl. And with that, we can use that, we can convert that from moles per kilogram solution to the fraction using one of those functions that we had previously, right? And then just once you get the fraction value, right, mole fraction, we can import it or include it as part of the input to the Dirichlet function. So you can easily run this. When you run this, this will give you the mole fraction of that, the equivalent mole fraction of that mole per kilogram solution of NaCl, and the density, viscosity value, all of those are internal calculation that PyGCC based on Dirichlet model that I've been able to do, its capacity, specific enthalpy, and all of those different things. Okay, are we together? Okay. No worries. Is that good? Okay. I mean, what I would also recommend is try to run it on your computer so that we can ensure that, you guys are, okay. So we've done the calculation at 200 degrees C and 500 bar, right? So the next thing we want to be able to do is to examine the phase coexistence properties at in this case, referring to that critical temperature, right, of water, right? So when you do that, the first expression here, or the first line of code here, is to find at that critical temperature of water, what will be the critical fraction of NaCl within at that particular critical water temperature, and also the it's called the three-phase pressure of vapor liquid, the coexistence of those vapor liquid and halite, right? So you have vapor liquid solid, right? NaCl, halite within the coexistence of that, the pressure at which those three phases would coexist, right? At that particular temperature. Then at a point where we now have a particular pressure condition, what fractionation of that liquid or of NaCl will be in the liquid phase, what fraction of that will be in the vapor phase, right? So those are the calculations we want to be able to do here. And also here is just to show how by adding some fraction of NaCl into our water, that increases or that changes your critical properties of water in that instance. So if you run if you run this particular cell, that shows you, like in the first instance, right, at 350 bar, right, you see the pressure at which those three phases would coexist, right? That's the pressure, and the critical fraction of any cell within that is 0. At this particular temperature and pressure, this is the fractionation, right? This is how much NaCl you'd expect to be in the vapor phase, and this is how much you fractionate to be in the liquid phase. And also you can convert that to molality just by adding this component, this amount of NaCl within that. You can see that we moved the critical point of water from about 350 to about 3 no, sorry, by the critical point of water is about is this condition, right? The 373 and 220 bar, right? And what we see is that at 400 degrees C, right, that would increase by adding this amount of fraction of NaCl within that would increase the critical condition, or you can get the two-phase coexistence above that particular critical point for water. So that's what we just showed with this particular example over here. And again, referring back to that table or the chart that Ben showed, right, in terms of the critical curve, right, then as you increase the fraction of NaCl within that, you can see that you continue to extend that critical point of water based on just adding NaCl within that. So yes, you can output entropy. So yes. So easily, like again, to know many of the let's see. Okay, if I do help, so that shows all the different parameters. So it returns the pressure of the three-phase coexistence, critical pressure of the water NaCl mixture, the critical composition, all of these composition for the saturated liquid halite density, the liquid NaCl density, molar volume, enthalpy, heat capacity, viscosity, and all of those different things that you can see. Okay, so now with knowing what the measured chloride is, right, what we want to be able to now figure out is to calculate the pressure, right, at some temperature that we can define that temperature range. Again, in this case, we're trying to find what points both the chloride geobarometer will intersect with the silica geothermometer. So we're trying to calculate what the pressure would be for all the different particular temperature range that we generate for this particular hydrothermal vent, right? So we have our mole per kilogram solution of chloride within this case. We are trying to use that based on that molality, calculate the fraction of chloride NaCl within that. Based on that fraction of chloride, we can then, because we are trying to calculate what the pressure would be, right? So we can range temperature. When we range temperature, then at the point where, based on the pressure that we are trying to optimize for, the pressure, the composition that we calculate that correlates with that particular measured concentration would be the pressure for that particular temperature. I know it's complicated, but I'm finding a way to explain. But again, the overall gist is just we are trying to minimize this particular function to calculate to get a chloride or a composition of chloride or NaCl for that particular temperature and pressure that matches the measured chloride concentration. So that's what we are doing with this particular optimization approach. So if we run that, that ranges the temperature pressure from the temperature from 350 to 610, and then based on the and then trying to calculate the pressure that will match that chlorinity of 0.757 mole per kilogram. So when you run that, that could take some time because it's trying to do minimization, right? There is a bound. So that bound is set by the pressure at the three-phase coexistence, the minimum range of that, and the maximum range, the critical pressure at that particular, at the temperature, at the critical pressure that bounds that particular temperature, and is using that to bound the pressure range and use that to minimize or achieve the same chlorinity that is equal to the measured chlorinity value. So if you run that, that should probably take, shouldn't.
Can you use this code reverse maybe to calculate the salinity from heating experiments?
Yep. That's what Yuri was doing, right?
Yeah, you can do that too. Again, like the Dirichlet function, right? It's embedded there that you can, based on your temperature pressure, you can calculate the concentration. You can go back and forth. Okay, so based on the optimization, right? So it generates the temperature, based on the temperature values that we've given it, it calculates what the corresponding pressure would be, right, for that. So looking into that, this particular example is for the quartz buffered system, right? And the quartz, again, going back to the dissolution of quartz to silica, right? And when you rearrange that particular, when you rearrange that, you'll be able to generate or calculate what the activity of quartz to silica is based on this. So in this case, we can then go back to our database because we need those Gibbs energy, right, for quartz to be able to calculate the activity of silica. So if you run this, mounting your, again, to tell you to connect, then again, hopefully you don't get error here because this was the past that I went over again. This folder, just make sure it's corrected and that should run nicely. So yeah, do you want to explain the shock data?
No, that's no.
Run it. Okay. Okay. Because we have different thermodynamic data sets that is also embedded within our thermodynamic database. So in this case, we are using this particular one. So based on that and based on the temperature pressure that we've generated, right, from this particular from this setup, right, we have the temperature range, pressure range, right, that corresponds to that chlorinity value, right? We are now using that to calculate what the activity, the log K, right? The log K for that saturation, and we use that log K to be able to calculate the activity of silica within that. So here, this particular expression is what we're trying to get. And once we get the activity of silica, we have the activity of silica that I've calculated based on the cut saturation. The challenge with that is that for this particular hydrothermal system where our silica is not buffered by cuts, we have this mineral assemblage that we have to also take into consideration. And that mineral assemblage requires that when we calculate the activity of silica from here, right, where we have the log K of this particular reaction, when you rearrange this reaction, you'd see that everything to be calculated for, then the activity of water will be within that. So when we do this, we'll be able to get what we refer to as, sorry, just a moment. So the activity. So what we're trying to get is we're trying to go from a cut buffered system to a non-cut buffer system, and we're trying to find what the activity ratio within that, and we're trying to use that to define the activity coefficient. The difference between that will now help us to be able to define the activity coefficient that we can incorporate in our silica geothermometer calculation when we are now trying to, because what we've done in the past is to find the temperature pressure, right, for chlorine, right? We need to find temperature pressure for silica, right, and find where they particularly intersect. So that's what we're trying to do with this particular approach. So again, if you run that, don't want to go into the details. So if you run that, based on how the equation had been written over here, there is also the Fournier empirical cut solubility in NaCl water. Again, that's an empirical correlation that also been generated that we can use. So all that, we're using that to be able to calculate what the activity coefficient is. And based on those activity coefficients, we know what our activity coefficient of the buffered mineral assemblage, then we can use that to be able to predict what the molality of silica would be. Okay, still running. Then based on that, okay, I think it's finished running. Okay, so based on that, based on the Fournier silica activity, we calculated the activity coefficient, and using the activity coefficient and the mineral assemblage buffer system that we developed, or that we consider, we're able to calculate the molality of silica within that. And based on that molality of silica, we're now using that to compare the measured silica from our vent fluid, and then based on the temperature pressure of our chlorinity that we've calculated, then we are then finding a path where the temperature pressure coincides with the activity of the silica that we're able to generate for that particular measured silica value. So that's why you see we go from the temperature pressure that we've estimated, the activity coefficients for silica that we've calculated, the predicted based on this particular expression, right? The predicted molality of silica, and we are trying to get where the molality of silica is about 7 millimole, right? So you see that 7 millimole is going to exist between these 2 points, right? So just interpolating between that, we're able to arrive at what the reaction zone temperature and pressure condition is.
So we are coming to the end of the session here. So a couple of things that I want to say. we can calculate, we can do all kinds of interesting stuff for activity coefficients. We had to figure out how to do that so we can do these simulations at higher temperatures and pressures that aren't at the normal 300 degrees or below 300 degrees, which is the normal database temperatures. So we've done that, thermodynamic peaks and activities, and we have ways of calculating the Bi-Huckel parameters. And fortunately for us, the Bi-Huckel works a lot better at high temperatures and pressures because most ions are complex. So ionic strength goes down. So it actually does turn out working pretty well. We saw these briefly before, but the Bi-Huckel, B, the Bi-Huckel are calculated in the code as well. And we'll show you this example here in the basically just really quick and easy to show you what we can do at the end here. And I'll just point out, because that'll get us to the end of the hour, we urge you to take extreme caution with the density extrapolation. You already saw how crazy it can do. And also the other thing that we really want to emphasize is PyGCC is a calculation tool. We do not make thermodynamic data. If we make thermodynamic data, you can cite our paper where we made the thermodynamic data. Don't cite PyGCC. We should not see, and I have seen and told people in the editorial process to not do this. We should not see Awolio and Tudelo as the data source, right? We are not a data source. We're using other people's data. We're just doing the calculation. So you can certainly cite our tool, but please don't cite us as a thermodynamic data set because we aren't one. Yeah, and so in the last couple of minutes here, I'll let Dapo very quickly show you the FreakC capabilities, and then we'll have, I think they're giving us lunch as part of the workshop fee, so that'll be nice.
Okay. So we can open the FreeQC integration with PyGCC. Again, we've talked about developing these databases. So when you develop databases, you want to be able to then go ahead with your geochemical calculation. So a good way, or one of those free tools that is freely available that you can easily integrate, is FreeQC. In this example, we're just going to use FreeQC that you can also download or you can install from PIP library. So yeah, again, same approach, installing FreeQC and PyGCC together. And some of these other components is just the DLL library that helps you to be able to, because FreeQC is developed in C++, right? So in C, those library, sorry, not C, is it Fortran? Sorry, I don't know. I can't remember if it's Fortran or C, but those library, you can easily just refer to those library, and that helps you to be able to do the calculation that you need. So again, same way, don't forget about this guy. And with that, you can easily just run your code. So here is just a function that helps you to be able to generate your database, right? So you can do everything at a go. We generate a FreeQC database. I'm going to zoom out, sorry. We generate your FreeQC database, right? Then you can run your FreeQC based on the DLL library that you've now generated. So based on that cell, right? So if you run that, hopefully you should not get any error. Okay. I'm just gonna, let me see. Okay, again, connecting because we are mounting. Okay, so the setup is complete. The folder has been mounted. The function to be able to run FreeQC is also created. So yeah, it's just an approach that we've talked about in terms of how you create a FreeQC database, right? So I'm just going to run that. I'm not going to go over that. Just creates our database that we need for FreeQC. You can open the database here, and that just shows you the line of the first line, or you can just go here and you see output FreeQC, right? The new database that we just created. Then this is a simple calculation, aqueous reaction with FreeQC. Hopefully everybody that is familiar with FreeQC understands the data set, like the data input format for like whatever you have .in, right, that you can generate. So if you go to any of those FreeQC example, just copy that and put that within this particular cell. Let's see, go down. Yeah, so if you just copy that within this particular code will run for you. So again, your database, specifying the directory where your database is, the database that we've generated. So I'm going to run that. Okay. Then now my input function for my FreeQC to do my simple aqueous reaction. In this case, I have 1 millimole NaCl, and I'm just trying to react that with potassium phosphate, dipotassium phosphate at pH of 7 and 25 degrees C. And when I run that simulation, again, this code runs the FreeQC simulation, right? Again, everything that you need, the input file, the database, and the library, right? That helps you to be able to run that. And all of that is just output into a data frame where you can now then do nice plotting of your, or you can see your result or everything that you're generating within that. So this will give you that for this particular case at the first case where we are reacting, where is it? Where we are reacting, there are two cases in this case, in this particular. So we have this reaction with potassium, monopotassium phosphate and dipotassium phosphate. And when we run that, we're able to see what the pH, the initial pH, right, for the water, right? This is what the initial pH, the PE for the water as well, at the temperature and all the different components within the initial water, right? And after that reaction, the pH dropped, right? As you can see, and you can see now you have more potassium and phosphate and all of the different components within that. Also the conductivity of your water also is also reported within this density and all of those different things. So that's a quick way based on your input, based on your data structure from FreeQC, right? Your database, you just put all of that together. When I was putting this together, I also saw that there is also a nice way where if you if you want to be lazy, you don't want to modify anything, right? You can just modify this cursor, change the concentration of the different potassium phosphate or dipotassium phosphate within that, and that would help you to be able to recalculate, right? So as I change that, right, you can see it does the recalculation of so this is a case where I now modify dipotassium phosphate within that from 1 to about 0.2. If I do that, as soon you see that the recalculation is done. The second one is the seawater mixing. So this is a typical example from FreeQC, I think example 3, where you are equilibrating a groundwater with CO2, a PCO2 of 10 to the power of minus 2. And you're also doing a mixing between groundwater as well as seawater, and you're equilibrating the mixture of that mixture with your calcite dolomite and also calcite only case, right? And you're calculating your saturation index. So again, for this particular case, I'm generating my database at steam saturation pressure between 0 to 300 degree centigrade. And again, example 3 from FreeQC, copied, paste into that, and run. Okay, then I can now run my calculation based on the same setup with FreeQC. And what you can see is number one will be my initial solution, right? So my initial solution, initial pure water, the pH is 7, PE, and all of those things. When I do all this equilibration with CO2, blah, 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 seawater mixing, the mixture, that changes and all of those different things. Then I can do nice plotting to be able to see how pH changes as I do that equilibration and all of those different things. Saturation index, I can also plot that with respect to those equilibration that you can see. This is another example with ion exchange. If you run that easily, I won't go over all of that, but easily you can just run and see how with your time step. So this is like doing like a transport related, so like a ion exchange transport and trying to track that time step with respect to the exchange between calcium and sodium in this particular case.
So you'll have all of those. If you ever want to use the speciation capabilities of FreakC, which is a free software, we've made these examples. Hopefully you'll find one that can be adapted for what you'd like to do. And that's the end of our 3 hours. So I hope everyone learned something here this morning. And yeah, please feel free to come up and chat if you'd like to talk about your application. Otherwise, yeah, we're always available by email and so on to make sure that whatever application you want that you think is possible becomes possible with PyGCC. So thanks very much.